I wanted to show you a second illustration or second example of dimensional analysis. The one we discussed in class was dimensional analysis of a falling body. We were able to show that the distance traveled by a falling body was in proportion to the square of the elapsed time for the falling body. Alternatively, you could express that as the time taken for the falling body to fall is in proportion to the square root of the distance that it falls. So a second important example of dimensional analysis concerns what we call the simple pendulum. Simple pendulum is just a mass, an object, a body on the end of a string. And that mass or that body, that object just oscillates, swings to and fro. That's a simple pendulum. And a simple pendulum has a characteristic length. So the string has a certain length. The string has a characteristic length. And it has a characteristic period of oscillations, time to complete one oscillations. And you can show by dimensional analysis that there's a simple relationship between the length of the pendulum and the corresponding period of the pendulum. In particular, the period of the pendulum is in proportion to the square root of the length of the pendulum. So that's like the distance, time taken to fall was in proportion to the square root of the distance fallen. So for our simple pendulum, dimensional analysis tells us that the period of the pendulum is in proportion to the square root of the length of the pendulum. That means supposing you had two pendulums, and one pendulum had 4 times the length of the other pendulum, then that longer pendulum would have the square root of 4, which is 2 times greater period. And so we're going to test that prediction of dimensional analysis. To do that, I've got 2 different pendula on the bench here. I've got a short pendulum and I've got a long pendulum, so 2 different lengths of pendulum. And actually, I've arranged it that the long pendulum is 4 times the length of the short pendulum, or the short pendulum is a quarter of the length of the long pendulum. So our prediction is that the long pendulum will have twice the period of the short pendulum, or the short pendulum will have 1/2 the period of the long pendulum. So here are the 2 pendula. Just measuring the short pendulum, its length is 12 centimeters. Now measuring the long pendulum, its length is 48 centimeters. So indeed the long one is 4 times longer than the short one. The long one's period should be twice as long as the short one. Let's try that out. So you can see the 2 pendula oscillating to and fro. And the long one is obviously oscillating, completing one period, completing one complete cycle at a slower rate than the short one. The short one is completing a complete cycle, a complete period in a much faster rate than the long one. And if you slowed down the video and counted the number of oscillations per minute, you discover that the short one has twice as many oscillations in a minute. The longer one has half as many oscillations in a minute. That is, the short one has half the period. So it does twice as many oscillations in a minute. The long one has twice the period. So it does half as many oscillations in a minute. So just watch them swing to and fro and try and count the oscillations per minute. Try and count the period corresponding to the two pendula. And that is a prediction. It's a famous prediction of dimensional analysis.